This is the next video in a playlist that I'm calling Introduction to Biostatistics using R. We're in Chapter 2, Descriptive Statistics, Part 5, and we're looking at measures of dispersion. Measures of dispersion essentially tell us how spread out the data are, or the variability in our data, and there's several measures for it. The first is the range. It's a very simple statistic or measure, and it's the highest minus the lowest data point. So that number, the bigger it is, the bigger distance between the max and the min, and that gives an idea of how spread out the data are. The next one is called the variance, and it is precisely the average squared distance from the mean. Each observation's distance from the mean squared, averaged. That's the variance. Now the sample variance, you'll often hear people describe it as it's the average squared distance from the mean adjusted for bias. And that adjustment for bias deals with the degrees of freedom associated with it. Now, I would encourage all of you to take a multivariate analysis class where we can look at the definition of degrees of freedom very precisely. And it has to deal with the rank of a matrix where the statistic is written in what's called a quadratic form. Now, in lower level courses or courses that aren't multivariate analysis, they describe it as the number of values in your data set that are independent. Another way to think about it is that however many, so n is the sample size, and then you subtract however many parameters you have to estimate from the population setting. So if we're looking at the average squared distance from the mean, so this is the distance from the mean, every data point squared, and then we're averaging it adjusted for bias. But this is not the population mean, so we have to estimate the population mean, and we're estimating one parameter, and so that's why we subtract 1. And so the degrees of freedom would be n minus 1. Now, if we look at the population variance, that means we know every single data point, all capital N of them, and we're looking at the squared distance from the mean. Here, we're not estimating the mean because we know it. We know every single value, so we can calculate it very precisely. And then we just average the squared distances from the mean. So the standard deviation is the square root of the variance. And the reason that we do that, one, it's more intuitive. So if whatever units our data is described in, when we square it, we get squared units. So if we're looking at miles, the variance, the units of the variance is squared miles, which is not very intuitive. So if we take the square root of the variance, then the units become something that we understand better, I think. So it's a more intuitive. And so the standard deviation is the square root of the variance. So this is the sample variance here. And again, we're adjusting for bias. And so the minus 1 is because we had to estimate that parameter. Now the coefficient is it's the standard deviation relative to the mean. And it's a unitless measure, right? So there's the units on standard deviation and the units on mean. Those units cancel out, and so the coefficient of variation it's a unitless measure, which allows us to compare different variables, with one statistic. And so we can look at the stock volatility and compare it to the medical test precision, just with the coefficient of variation, because there's no units in it. Now, percentiles and quartiles, they're what are called location parameters, meaning they describe a position in the data set. So if we're going to look at the p percentile, and we have n observations, and let's assume they're sorted in order. So it's the value that p percent of the data to the left, and then 100 minus p to the right. That's the pth percentile. Now, quartiles are percentiles, but we're dividing it into fourths. So the first quartile is the 25th percentile. And remember, we're finding positions. So this is the n plus 1 over 4th position or value in a sorted data set. And we represent it by Q1, the first quartile. The second quartile is the median, which is the 50th percentile. And again, remember, it's a position in the data set. Third quartile is the 75th percentile. And this is sometimes not an integer, so we don't know its exact position in a data set. So if we get 6.3 as our, say, the first quartile, then we would take the value in the 6th position and the value in the 7th position and average those two values. So this, if let's say the 6th position is, I'm making this up, 2.3, and the 7th position is 2.5, then when we average them, the first quartile would be, we average those and we get 2.4. And so that is the first quartile. Now, the interquartile range describes roughly 50% of the inner variability of our data set. So we take the third quartile minus the first quartile, and that's the IQR, the interquartile range. So let's look at that. Let's first calculate the range. So we take a sample of size 100, and the range is the largest or the maximum minus the minimum. The range returns it's a vector of length 2, which is the minimum value and the maximum value. That's what this function returns. So if we use the diff function, which is used quite a bit in time series analysis, it takes the max minus the min, and then that's the range of our data set, of our sample. Now the sample variance, we just use the var function and we get 0.75. Now to calculate the population variance, R doesn't have an argument that you can put in here to say divide by n, not by n minus 1 adjusted for bias. So you have to trick it in a sense. So let's find the length of our data set, how many observations we have. And you have to be careful there, because if one of those values, one of those components is missing, the length still counts that. And so you have to make sure that it's non-missing. But we multiply it by n minus 1, which gets rid of the divisor in this, and then we divide it by n, and then that's the population variance. SD is the sample standard deviation. Of course, we could have taken the square root of the variance, and those would be the same. The coefficient of variation is the standard deviation divided by the mean. We take it times 100 to get a percent, and then this is it. And so we get a negative value because our the mean is negative. Now, some create a definition of the sample coefficient of variation as the absolute value of the mean, and that way we always get that as a positive value, and that's okay. Now the quartile function returns the quartile, so it's the minimum, the Q1, Q2, Q3, and the maximum. Now we notice that I'm storing this information in a variable called temp Q, which I temp quartiles, and the outside parentheses tell it to print the results. If without those, it would just store it and it would be silent. You wouldn't see it. So we want 1, 2, 3, the fourth value in this vector minus the second value in this vector, and this is the interquartile range. Now you could use IQR, which is part of that moments package, and just say the interquartile range of our data set, and notice they're the same. Now we don't have to use the quartiles. We could tell it any percentile that we want. So we want the 10th, the 20th, 80th, and 90th percentile, and it's going to pump out those values. Now kurtosis tells us how heavy the tails are, the tailedness of a distribution, if that's a word, I don't know. And it's all relative to the normal distribution. So if we have a normal distribution, then the kurtosis would be 0. Now, if we have a t-distribution, which has fatter tails here than the normal, then, first of all, the normal distribution is called mesokurtic, and so that we get a value of 0. And the default function in R, well, I'll explain that in a second. Now, leptokurtic says that the tails are heavy. So this t-distribution will have a positive value for kurtosis, meaning it has fatter tails, which means we're more likely to see observations out here in the extremes. Platykurtic it would be negative, which means that the tails are thinner than a normal. So this would be a platykurtic. So it's low kurtosis. And notice I have this. So these are the formulas. Now, most books provide this as the definition for kurtosis. And notice that we're subtracting 3. And that forces it to be 0 if it's like a normal distribution. It's positive if it's leptokurtic, meaning it has fat tails, and skinny tails would be negative. Now, the formula in R does not subtract this -3 here. So it's all relative to 3, and that's what these describe here. So to follow, I think, what most books use, which is this -3, let's do an example. So let's take a random sample of 1,000 from a standard normal, and let's look at its kurtosis. Remember, we have to subtract 3 to follow this formula, and we get a value of 0.1, which is sort of close to 0, which makes sense because we're sampling from a normal, which should have a kurtosis of 0. Now, leptokurtic, meaning it has fat tails, we're going to randomly sample from a t-distribution, 2 degrees of freedom, find their kurtosis, and it's a positive number. So it has fat tails. Now, if we look at a platykurtic or thin tails, we usually a uniform distribution, and I'll create plots of these. It's a little confusing, but let's look at the kurtosis of this uniform, the random sample from a uniform distribution. I only have max from -3 to 3, and it's negative, so it has thin tails. So let's look at what's going on here. So we plot the normal curve, the t curve, and this uniform. And so this is the normal distribution, which is here. And the t-distribution, notice that the tails are fatter. That's leptokurtic. So the kurtosis value is positive. And a uniform is kind of weird. That notice there's like really nothing in the tails, or it's flat. And so it technically has a platykurtic kurtosis or value of in the negatives. Now, the box and whisker. Now, I pretty much call it just box plots, but I guess it originated by what's called a box and whisker plot. And I've calculated tens of thousands of these for reports. They're very helpful, very descriptive, and people just love them because it summarizes the data quite well. So the keys to a box plot, there's essentially 5 or 6 or 7 different measurements here. It tells us the minimum, now excluding outliers, and I'll show you that in a minute. It plots the first quartile, the second quartile, the third quartile, and the maximum value, excluding outliers. And then the whiskers extend to the minimum and max, and then it also plots potential outliers. And there's formulas for these, and talks about, how many, standard deviations above the mean, and some define it as, the distance above the third quartile, or, there's different formulas for that, but they're all pretty similar. So we take a random sample of size 10 from a standard normal, we box plot it, and then we store all the calculated values in this variable BP, which stands for box plot. And we get this plot here, not the numbers just yet, But notice that this is the maximum value, this is the minimum, this is Q1, this is Q2, this is Q3, and to put these numbers beside it, we use the text function, which adds text to a plot. I put it at the X value of 1.3 because I knew that this was a 1. And I accessed the stats. This is the X value. These are the Y values. So in this BP, there's something called stats, which are these values. And then I put the actual values. I round them to 3 so they print nicely. Otherwise, you get 8 decimals or whatever they are. And these are the values. This is a box plot. Now, usually I don't see this in the plot. I was just illustrating it, and you use the y-axis for the different values. So now let's create a box plot of these distributions. So again, we're going to create a plot that has 1 row and 3 columns. So there's going to be 3 plots side by side. And let's just do the box plot of our normal sample that was sampled from a normal or a uniform or a t-distribution. And we look at this, and so this is a normal distribution. Now notice these extra dots. Those are potential outliers. Now, we're not saying that they are outliers. They're potential outliers, and that's the beauty of what the box plot creates. In the uniform distribution, well, there's no outliers. So that's the max, and that's the min. This is the first quartile, the second quartile, the third quartile. And actually, you can kind of tell, like if the median is up here, you can tell that it's a slightly skewed distribution. So there's different things you can glean from a box plot. And here's a t-distribution. Remember, the t-distribution has fat tails. So there's potentially a lot of outliers. And this is a t-distribution. Notice the scale goes from -20 to 20. The mean is 0. So there's potentially a lot of outliers. Okay, well, that's all I have for this video, and we're going to start chapter 3 in the next video.